We are live now. Good day to all. A warm welcome to each and everyone who have gathered for SSE E Talk series conducted by Saveetha School of Engineering, Saveetha Institute of Medical and Technical Sciences. Today's talk will be the 20th talk of the series. I am Dr. Deepak Arun, Associate Dean International Affairs, Saveetha School of Engineering, Saveetha Institute of Medical and Technical Sciences. At the outset, I extend my sincere thanks to our Honorable Chancellor, sir. I also extend my thanks to our Director, Madam, for Madam's kind support, guidance, and motivation in conducting this event. I also thank Principal Sir and Vice Principal Sir for their guidance and support. Today, we have with us Dr. Fawad Inam, Professor and Head of Engineering and Computing, University of East London, UK. Dr. Fawad Inam is a Principal Fellow of the Higher Education Academy, UK. Professor Inam is among the 1% full professor of 92,915 academics under the age of 40 in the UK. In 2018, he moved from Northumbria University to East London as the Head of Engineering and Computing and Professor of Mechanical Engineering. At Northumbria, he was steering engineering portfolio as Program Leader, Director of Engineering and Associate Head of the Department from 2013 to 2018. Prior to that, he led Composite and Aeronautical Engineering programs at Airbus Advanced Composite Training and Development Center between 2011 to 2013, where he contributed towards the development of Airbus A350 jet planes. From 2005 to 2011, he developed commercial products like Sugru and Key Armor nanostructured materials for British defense purposes as R&D technologist for Nanoforce Technology Limited in London. Professor Inam is in receipt of two aggregated postgraduate teaching qualifications and recognized as the one of the leaders in engineering curriculum design and technologies. As an active member of Engineers Professors Council, he has advised quality assured over 45 different universities and institutes from all the four nations of the UK. Professor Inam has also influenced institutional higher education practice in other countries like China, South Korea, Singapore, Malaysia, India, Pakistan, and Saudi Arabia, to list a few. With over 150 research outputs, H index of 30, and funding over 2.5 million pounds, he has presented several keynote speeches at various leading international conferences. Professor Inam's research expertise is primarily around improving the performance and functionalities of engineering products using material science and engineering, in particular nano-influenced smart materials. He is a regular peer reviewer for a dozen research journals and examines PhD theses in the UK and overseas. He is also the recipient of Materials World Award confirmed by the Institute of Materials, Minerals and Mining in 2008. I am very happy to welcome once again Dr. Fawad Inam to give invited talk on the topic, Come Fly With Me in a Plastic Jet, in our SSE E Talk series conducted by Saveetha School of Engineering, Saveetha Institute of Medical and Technical Sciences. Over to you, Professor Fawad.
Thank you very much, Dr. Deepak Arun. That is very kind of you and very polite and comprehensive of you to just go through the introduction. So, as you have, I'm first of all very thankful to your good self and the senior management at SSE to award me this opportunity to highlight some of the great research work that I have been involved with and how it is benefiting the community as well as the wider aviation industry. So I am Fawad. As you mentioned, I'm working for University of East London. And we are based in this very beautiful part of East London. As you can see, the campus in the shared slide. And we are a university for people primarily for our East London communities and beyond. And we are one of the 130 universities in a very small United Kingdom. So it's higher education is very important to the government agenda, and we are fulfilling it in many ways. And I'll be describing the research I have done at the same time, educate you in about this great materials revolutionary technology that we are seeing now in practice, and how our students are also benefiting in terms of our teaching informed research. I'm a fellow of IMEC-E, which is Institution of Mechanical Engineers. I'm a chartered engineer. I'm also a principal fellow of British Higher Education Academy. So that simply means that I have this responsibility to ensure that technology is there, it is being upgraded, it is being researched at the same time. And at the same time, I have this higher education hat to ensure that our students, the future engineers, like my audience today, are being benefited from the great work, from the great research work I'm part of. So I came up with this very interesting topic, come fly with me, in a plastic jet. Yes, I'm referring to a commercial aircraft, which is made fully of plastic. And I'll be explaining you about how it was developed. It's now in running for almost 10 years. And I was very lucky to be involved in the actual development of the materials technology when I was working for one of the companies from one of the manufacturers of aircraft. That's Airbus, which is the European equivalent of American Boeing industry. So I'll jump on to the next slide. So yes, just about me. I'm based in London. Okay, if you want to know more about me, you can find me on Google very easily as well. I was working at Airbus. Okay, sorry. I think if all can mute themselves, that would be much appreciated. So I was working at Airbus, which is located, as you can see on my slide. It was actually it's still there in the Northeast Wales, and I was working there for between 2013 to between 2010 to 2013, and that is where I was working on the development of the product which I'm going to talk about today. You can see this is where London is, so it's not that far away. It's a 3-hour by train if you want to get a sense of the geography where I was involved. Okay, so this is the aircraft I want to talk about today, A350, and because we have a huge population of our students in this webinar, I have really scaled it down so that you understand what is really happening. If you have basic understanding of physics and chemistry, you can understand what I'm talking about today. So this is the story of this revolutionary commercial plastic plane. Yes, it is made from plastics, from thermoset plastic or thermoset polymer. As you can appreciate that the former technology, which is still very much in action, aircraft fuselage, aircraft wing box, is having aluminium lithium alloy. However, because of number of reasons, in particular weight saving, in particular having less fuel burnout, technologists came up with the idea that why don't we use carbon fiber reinforced polymer plastic for this great commercial product. And as we all understand, whenever there is a new aviation technology, There's quite a lot of government-based stringent research and certifications before you can see a commercial product of this nature in action. So I'm going to talk about A350 XWB, and let's just XWB stands for extra wide body. Okay, so it's one of the Airbus families. So if you travel, for example, on a single aisle aircraft, these are Airbus A320. So, for example, Jet Air, which is I know one of the commercial liners in India, and there are many others like that. So these are single aisle aircrafts. It just means that you have like single aisle, you have 3 seats on right, 3 seats on left when you enter. That is Airbus A320 family. A350 is a double aisle aircraft. So it means that just like if you're traveling on international route, you have the formation of 3 seats, 4 and 3. So it's quite a big. So let's look at the plastic aircraft that I'm trying to introduce today. So this is Airbus A350-900, and it's not just about the materials revolution in this aircraft. It's about a number of other factors that are also embedded in this technology. I can still hear some background, so I would advise everyone just to mute their microphone, please. Thank you very much. So let's just concentrate. What's so special about this aircraft? So as you can see, let's look at the engines. Okay, see the power generators, the Rolls-Royce engines. These are the latest generation, having very minimal carbon footprint, and at the same time, they are quite fuel efficient. It is having what we call as a morphing wing design. So morphing wing is inspired by nature. This is how the birds fly. These are extremely flexible wings, which changes their shape according to the aerodynamic need of every stage, whether it's landing, whether it's cruising, whether it's taxiing, for instance, or whether it's taking off. So it is very capable of changing its shape. It is very dynamic. The engines, again, they are quite quieter and quite fuel efficient. If you look at the wing design as well as the incorporation of sharklets, so if you look at the wing tips, this blue tips at the end of the wings, these are called sharklets. These are very much inspired by nature. And this concept is called biomimicking. So biomimicking simply means that you're copying Mother Nature, which is doing engineering since the beginning of this universe, whatever and however you could go back. So there's quite a lot of learning that could be done from nature. And this great product, this great aviation product, has got a number of these features that are purely inspired by Mother Nature. So when we look at the sharklet, for example, as you can see that sharks, they have these fins, which have one of the principal reasons for them to have fins. One of the functions is to give them easy drag in fluids, or in terms of aircraft, it makes them more aerodynamic. It saves on fuel. So this is again a feature that is inspired. This is copied from Mother Nature, and at the same time, this whole concept of morphing wing. So it's a great product. It's not just about materials revolution in this engineered product. It is also about the design, because engineering is all about design as well as about selection of right materials. If you don't get any of these right, your product, your system is not appropriate, is not optimized, or could be very likely to fail as well. So This product is taking into account some revolutionary design engineering principles and at the same time some excellent material. And this is exactly how it is made. It is simple. You can purchase epoxy, which is a thermoset polymer. Okay, so super glue, for instance, you have part A, you have part B, you have resin and you have hardener. You put it together and then you mix it and then it cures. It becomes hard. Okay, it stabilizes. It cross links all the molecules. They cross link and it becomes a brittle polymer. And you mix it with carbon fiber. And this is exactly how this aircraft, the fuselage, as well as the outer skin, as well as the wing box are manufactured. And this is a plastic because primarily you're using epoxy, which is a thermoset polymer, and again, you can imagine the amount of weight saving. So if you're wondering, aluminium, just for your curiosity, steel has a density of around 7.6 grams per centimeter cube. Um, Density, as we all know, is mass per unit volume. Okay, so steel is 7.6. If you are comparing it with gold is around 20 gram per centimeter cube. Aluminium is around 2.3, 2.5 grams per centimeter cube. And this particular material is little less than 1 gram per centimeter cube. But we are not compromising on the mechanical performance. We are not compromising on the strength. We're not compromising on stiffness, as well as other structural properties that are expected of this material. And this is what we call as a composite material. For those of you who are not aware or who are not familiar with composite terminology, composite is a mixture of two different categories of materials. So you have fibers, you can have like a glass fiber or even natural fiber these days. There's quite a lot of research going on natural fibers. And you mix them with resin, which is a polymeric material, and together, once the resin cures, once it hardens, you end up having a solid structural material. And this is what we call as a composite material. Now, you can actually lay your fibers in a very different orientation. As you can see here, we have 0 and we have 90-degree orientation. You can create laminates. You can create sandwich structures and put them together, and they will collectively perform. So if you understand the science behind it, fibers, they are taking bulk of the load, whereas resin is serving like a glue. So it's a great materials strategy to create very strong, very stiff materials that can be served for these number of applications. So if you look at speed boats, for example, if you look at space satellites, if you look at oil and gas industry, for instance, and even performance sports. So example, even in your car tire, for example, it is rubber, which is reinforced by steel wires. So it is also a type of a composite material. Similarly, a baseball bat, a tennis racket, they all are reinforced nowadays with glass fiber and so on. And if you're wondering on the right-hand side, even for construction industry, composites are very popular. I can think about concrete, for example, which is a type of a ceramic composite where you have gypsum, where you have ash, you have stones, and you have cement, and which is like a glue, which is your resin, which is reinforced by solid steel bars. So it is again a type of a concrete, is a type of a composite material. You can see, apart from that, it's used widely in construction. So one of the largest clock tower in Saudi Arabia, for example, is actually having quite a lot of involvement, quite a lot of composite involved. And again, you get the great weight saving, but without compromising on the structural properties. coming back to my aircraft, and you can see that when I was working for Airbus, I was involved working directly in Bremen, in Germany, with a number of colleagues who were the chief engineers and chief scientists, and I was part of the R&D team in 2011, 2012. You can see that the aircraft, if you look at the X-ray of the aircraft, 53% of the aircraft is containing carbon fiber reinforced plastic. Okay, and this is replacing the standard mature technology which came in 40s and 50s, aluminium, a lithium alloy, and this is where you're making significant savings on weight. If you're wondering whether these aircrafts are safe or not, yes, they are fully operational. You might not even realize, but if you're traveling on the new 787, Boeing 787 is again a similar aircraft, or for Airbus, if you're traveling on A350, you may not realize, but all these aircrafts are fully in operation, and they have completed more than thousands of successful flights. So yes, they are fully safe, and it's again one of the great revolution that has dominated materials revolution. Because if you look at our history, we started as we evolved from Stone Age into Bronze Age into Steel Age. Now we call ourselves Smart Materials Age. So yes, we have been evolving, and we have been using materials in that particular era for benefiting our surroundings, for making our daily affairs more smart and more multi-purpose and fully functional, making our life easy, to cut short. So as you can see that the critical aspects of this aircraft still, the real in terms of stringent, very harsh objects. For example, you can still not replace titanium, which is holding the engines, because of course, if you do not have engines at 10,000 feet, this is a serious emergency in aircraft and aviation. So that's why you need a material which is extremely strong, even more than the carbon fiber. So we are still using titanium to connect the wing box with the engines. And at the same time, if you look at the leading edges, where there is a very likely a bird strike incident that could take place, you still have metal, because of high impact resistance, that is still higher, that is still superior when you look at the epoxy composite from which we are making the other structural elements of this great design. Obviously, if you're wondering what's going on with the cockpit, again, there's quite a lot of avionics, electronics, circuits, PCBs. There's quite a lot of communication equipment in this part of the aircraft, and it does have to be protected. Again, in case of a bird strike, or in case of any structural damage, you cannot afford to lose this very critical part. Hence, you still have a metal, purely because of high impact resistance. But if you think about the properties in general, composites, they don't fatigue. Again, fatigue is an engineering phenomena. For those of you who have studied materials engineering or solid mechanics, failure due to vibration is known as fatigue. This particular type of material, it does not fatigue. Because if you think about the fuselage, there's always like a hoop stress. You have to pump in more oxygen if you're at 10,000 feet, for instance. And then when you're on ground, you don't have to have that oxygen. So there's a bit of a hoop fatigue going on, where if you have a metal, it can actually fail because of this frequent vibration, or let's call it fatigue, cyclic loading. The material can fail. But in case of composites, you can pump more oxygen, and that's where the passengers have reported more comfort level because they don't have to, because the technologists, the manufacturers, they don't have to worry about the fatigue failures in this technology. So they can make the experience more comfortable for for its passengers, for the commercial passengers. So again, there are many advantages like that. Of course, if you have made the aircraft very lightweight, there's a possibility of nearly vertical takeoff as well for this technology. And again, this is a great feature which is offered by Airbus A350 as well as Boeing 787. If you Google, there are plenty of videos you will find where there are aircrafts doing uh, almost a vertical takeoff. And that is purely possible because it's easy to lift lightweight structures, because you can imagine you are saving almost 3 times the weight in comparison to the aluminium. If you just look at the density, as I was explaining, aluminium is around 2.5, 2.7 grams per centimeter cube, whereas this material is offering densities of lower than 1 gram per centimeter cube. So clearly, you don't need to be a rocket scientist. You can see that you are saving almost 3 times the weight without compromising on the properties of the material. So there are many
What's the carbon time saving?
advantages that could be offered at the same time. Okay, so in terms of the benefits, I have summarized here. I'm comparing some of the very renowned engineering materials. As you can see, if you look at steel, it is not light. It is heavy. It is having a density of more than 7, and that's why you don't use it as a structural material that much for aeronautical, for aviation. If you look at aluminium, it is very cheap for sure. Aluminium is cheap because of its maturity and because it's one of the most abundant metal available in our planet. If you look at the ores and mines, alumina Al2O3, it's widely available. That's why aluminium is quite cheap. If you look at, but it's not that strong in comparison to carbon fiber. It is not that lightweight, again, in comparison to carbon fiber composites. If you look at titanium, again, it is much more expensive. It's not cheap. However, in terms of strength, it is getting 3 stars in comparison to 2 stars for carbon fiber. And in terms of light, it is slightly heavier than carbon fiber. So now you can appreciate why, if I can go back, why do you need titanium in certain parts of the aircraft, and why you need aluminium because of the bird strike, and why you can afford to have a lighter option like carbon fiber. Obviously, the technology is relatively, when you talk about Air 350, for example, we are getting all these benefits, low amount of fuel burn, and obviously you can think about the overall benefits that if you have low fuel burn, if you have less reliance on hydrocarbons, obviously that would be good for our planet, because climate changes we all are experiencing now in different parts of the world. It's radically changing, and we need to do something about our climate. And obviously, when you talk about aviation industry, it's actually treated as one of the very dirty industry in terms of one of the chief polluters, because they produce quite a lot of carbon dioxide, which is harmful for the planet. So if you can, of course, burn less fuel, that is in long run going to help the planet. So this is again one of the motivations for technologists to move from the standard heavy products to lighter products that would require less fuel burn, and vice versa. If you look at the supply chain, again, it's not that straightforward process. Airbus is a European company, and there's quite a lot of engineering, supply chain, OEM involvement, liability, government agreements that are involved. So if you look at this product, The central assembly line is situated in Toulouse in France. That is where the headquarters of Airbus is in the mainland Europe. UK is only responsible for a number of parts in different areas. But one of the good thing about UK is that UK, if you look at the wing box of all the airlines of Air A350, of all the commercial fleet of Airbus company, you will realize that all the wings are manufactured here in the UK, as well as the engine. So UK is responsible for producing the most important, the most dynamic, the most critical parts of Airbus commercial fleet. Here in Broughton, where I was working in northeast Wales, just on the English border, this is where, if you think about the world's largest aircraft, Airbus A380, the double decker. Okay, if you travel to, for example, by Emirates, Emirates is having many of these Airbus A380s, the double decker. The wing box of that aircraft are also produced here in Broughton. And in Filton area and Bristol region, this is where the landing gears are manufactured. So the UK is involved in the smart objects, the smart components. And you can see that from the other countries. So we have quite a lot of involvement from Spain, from Germany, and so on. And at this point of time, there are around 3,500 engineers, apprentices who are working for the Broughton plant. There's a lot of politics going on with the company because, as we all know about Brexit, by the end of this year, United Kingdom won't be a part of the custom union. So there's quite a lot of politics and quite a lot of decision making going on behind the scenes because one of the beauty of European Union was that there were no boundaries, there were no border in the European Union, so you can trade without worrying about the custom tariffs or without worrying about the custom checks, and you can freely trade just as you are trading between different cities of India, for example. So that was the beauty of European Union, where the club, where the United Kingdom is now leaving the club. So I think it will have political and engineering implications. They may have to change the way how they are doing things. Now, I'll spend some time in just elaborating how we are bringing the research from industry into action, into our classrooms at the same time for the benefit of our students, and how, as a British university, we are working very closely with a number of our partners to ensure our students are benefiting from this state-of-the-art research that is taking place. So I'll give you some example here. I've got a couple of case studies here. Every aircraft gets struck by lightning once a year. This is a fact. And obviously, if you understand the physics of lightning strike, the way how it works, whenever there's a lightning strike, you need to have a conductive outer body that is responsible for dissipating, that is responsible for spreading the electric current around the aircraft. And this is how you diminish the energy from the lightning strike. And this is how you mitigate against the accidental event. I mean, I'm not sure if you have experience, but I had an opportunity once, well, a very rare opportunity once to experience how it's like in a test conditions. It's quite a horrible experience. The flash and then the sound. It's not a very pleasant experience if you are actually in an aircraft that is hit. But what I want to assure you that your aircraft, whether you're on a Boeing product or Airbus, is very much designed to ensure that it looks after any accidental incident of this nature. So let's look at behind the scene, what is happening. So normally if you have a metal aircraft, it's very easy because it's made of aluminium, and aluminium is one of the best conductors of heat and electricity, it's very easy to dissipate the energy around the aircraft. But in case of a non-conductive material, because epoxy plastics, they are non-conductive. Even we are putting in carbon fiber, the electrical conducticity of the product is not that like a metallic material. So what we have in place, if we actually put it under the microscope, if we just remove the carbon fiber, you will realize that there's a lot of copper that is embedded in this aircraft. Now, this is also a very critical part of an aircraft, by the way. If you're wondering where the fuel is stored, it's actually stored in the wing box. So the fuel of an aircraft is always stored just above the engines, and you have the stringers, spars, and ribs, and this is exactly housing the aeronautical grade gasoline, which is responsible for powering the jet engines. So you can see the yellow is expanded copper foil. Now copper has got its issues. As we all understand from our looking at a thermometer, how it works, you apply heat, metal expand, mercury is a metal. So, and when you apply, when you reduce the heat, of course, metals contract. So copper has this issue. If you think about a typical flight taking off from Dubai, let's suppose plus 40 degrees Celsius, going up at 10,000 feet, minus 50 degrees Celsius, landing in Heathrow, London, minus 2 degrees Celsius. So it is going through a cycle of plus 50 to minus 50, for instance. Let's put it that way. So copper expand and contract. And at the time when we were doing this work, we realized there's an issue because copper, being a metal, is constantly damaging the soft plastic, the soft epoxy. So we came up with a solution as engineers, which is now being embedded in the second generation aircraft, is to use some sort of a graphene, which is one of the nanomaterials. And at that time, I was involved in doing a number of research work where we were substituting graphene or graphene type material into the polymer. So, for example, you can see here carbon nanotube, which is again a type of a nanomaterial. And what we were finding, we were making the plastic, the epoxy, black as well as very highly electrically conductive. If we could do that, we do not have to worry about putting copper, as you can see in this particular slide. You don't have to worry about putting a different metal into a soft plastic because they were not very chemically compatible, and we were having these type of issues. So what we were suggesting at the time is that you could actually put nanomaterials, and you can see here, this is just an example of we were looking at the mechanical performance, and what we also realized that by putting copper, by replacing copper with carbon nanotube and or graphene, you're also making the product a bit smart. So what I'm showing here, we have a graph between electrical conductivity on y-axis, and we have a number of Vickers indents. So Vickers indentation is a test when you are trying to assess the hardness of a material. You have a diamond tip, and you actually create a notch like this, and you look at the dimensions to understand how soft or how hard the material is. And what we observed by doing these indentations, so we are creating more damage by having more number of Vickers indent. What we were observing that the electrical conductivity is constantly decreasing because of the indentation. So in this way, we can actually we started integrating sort of structural health monitoring, which we call, for example, here. So these are the big one are the micro-sized carbon fiber, and then we were dispersing carbon nanotube, which is the nanoform of a carbon, and we realized that all of a sudden there's no need to actually substitute to actually have a metallic material, a material that is quite hard for our soft and very brittle matrix. And at the same time, what we also observed that the material is responsible for having some improvement in the properties. Now, this was a very important research, and I was only allowed to publish the key scientific findings in a way that was acceptable by Airbus. Because obviously, if you're working on a commercial research, there are quite a number of intellectual property issues, because this technology, the time your company is actually owning the intellectual property. But what we were trying to get out of this, and this research is very much underway, and now they have created a product which is having the replacement of expanded copper foil for the actual wing box. There is a type of, there's one of the series, Airbus A350, either it's 900 or another series, which actually does not contain copper foil, and it's all influenced by this type of research that we conducted back in 2012 and 2013. And this is how we are bringing research from the industry into our programs. I would like to take this opportunity as well just to promote my existing university, where we are, what we are doing, and what makes us different. I explained about my experience at Airbus, the technology that I was involved in developing, and as a fellow of Institution of Mechanical Engineers, it's my responsibility also to bring those technologies, those case studies, into our classroom, into our lecture theater, so that engineers of future, like your good self, like my audience today, could benefit and come up with the next innovation to make to protect the environment, to make life easier and smarter for everyone. And this is again what engineering is about. Engineers are problem solvers of future. This is our great Docklands campus, by the way, as you can see on the bottom right hand side of the screen. We are the only university that is so close to an international airport. We are next to London City Airport, next to Asian Business Port. This is going to be the next Canary Wharf of London, the next financial district. And you can see that it's a very inspirational, award-winning campus we have. And we are having these number of programs. We also have our partners in India who are marketing these programs. I think for as an Indian student, it's a great opportunity. As an international student, it's a great time for you to come to the United Kingdom, in particular London, because UK has recently announced that any student coming to the UK in this September and onwards will be eligible to apply for a post-study work visa for 24 months. So that means once you finish your education, whether it's a bachelor's program or a master's program, you can actually apply and get a 24 month work permit without having a job, and your employer will just be seeing you as a local employee, like a local citizen, because you have the similar rights. So it's a great scheme. If you Google PSW or post-study work visa, you will realize it's open now for international students, and it's offering a great opportunity for all the engineers of the future, international engineers of the future, to get to come to the UK, study with us, and at the same time get a job, get into the UK labor market. And these are the different programs that we are offering as a university. As you can see, from mechanical, mechatronics, general engineering, construction engineering, management, biomedical, we have a complete suite of accredited qualifications that we are offering here in East London. With this, conscious of time, I think I have taken 45 minutes precisely. This is my email address. But again, if you would like to find me, it's very easy. you search my name, and you should be able to get my contact details. I would like to now open the stage, the forum, for our young students, in particular, the engineers of future, to ask question in relation to anything that I have discussed, or even if you have any general question, I'll be delighted to answer your questions. Thank you very much for your time. I'll open the stage now for Q&A.
Yeah, thank you very much, Professor Fawad. It was really a wonderful talk. You have highlighted various aspects of aircraft materials, different types of materials used in aircraft, and what is the latest thing happening, materials which are used to reduce the weight as well. So now the stage is open. Whoever is having queries can ask Professor.
Hello.
Yeah, please introduce about yourself. Yeah.
Yes, sir. Professor Fahad, I'm Dr. Sylvester. I'm faculty in mechanical engineering. Yeah, my question. Hello.
Yes, carry on. Good to
Yeah.
hear from you.
Yes, sir. The thing is, I have, two questions, but ask one by one. Well, first one is actually you are reinforcing the fibers. So, carbon fibers. So, aligning or reinforcing in a particular manner is actually kind of difficult part of the composite, or how do you do it?
Okay, so we have a method called tape layup. So you start with the pre-pregs. We are actually for this particular aircraft, there are a number of suppliers, primarily based in Germany. There's a company called Hexel. They make pre-pregs. So what is a pre-preg? You have partially cured epoxy resin that has already been pre-mixed with the tapes of fiber, and then you are putting the spiral, the rolls into a tape layup arrangement, and it's simply just laying up the pre-preg, the pre-cured fiber on the mandrel, on the skeleton of the aircraft, and then you're putting the whole thing in an autoclave oven, which is high pressure, high temperature curing. So so that is how these are actually manufactured in Broughton plant.
So in a bulk production, we can do it. So by using this method.
That's right. That's right. I mean, this is exactly how they are making fuselage. They make all these small different parts, and yes, you need a very large oven, a very large autoclave, which comes with very much health and safety implications, because you have a pressure cooker, which is extremely large. So it's like having a bomb in your factory. So yeah, but you can do that for sure.
Yeah. One more thing, actually. So you are reinforcing the carbon, and in the other case, you have told okay, in between the carbon fibers, if you are able to put the CNTs, carbon nanotubes, which are in very smaller in size. So yeah, exactly here. So in this particular case, can we orient in a particular manner as you are doing for glass fibers? So,
At the time, I think I got your question, Dr. Sylvester. The time when I was doing my PhD, it was all about orientation of nanomaterials in epoxy and in ceramic. And as you can see here, whilst the whole intention here is not to have any isotropy or directionality in our matrix. So we are randomly distributing, because to separate, when we talk about the size, the diameter of my micro-sized carbon fiber is around 5 micrometers, which is the size of your hair. And my nanometer, my carbon nanotube, it's around 15 to 50 nanometer in size, in the diameter. So we are talking about something very different here. So the whole intention at this point of time was to make things more electrically conductive and come up with a homogeneous epoxy resin. We used to call it the black resin, which is having the pre-dispersed carbon nanotubes. And then we were trying to create pre-pregs out of it. But we were we were looking at the yellow epoxy, the raw epoxy without having any nanotubes, and the black epoxy. So we were having a randomly distributed, but yes, there are different techniques. If you metallize your carbon nanotube, if you are using techniques like apply very high magnetic or electrical field, so you can have some sort of orientation, or for thermoplastic, for instance, if you are doing extrusion or injection molding, there's a way how you can stretch your fibers and you can create some sort of alignment. But that was not the purpose of this work. The purpose of this work was purely to have homogeneous material containing, which is having homogeneous electrical conductivity. So whether you test it like this or you put your 2 point ohm meter like that or like that, the electrical resistance should be equivalent. That was the intention of this work. Thank you very much, Dr. Sylvester. That was a very good question, by the way.
Can I ask you one more question? Dr. Deepak, I have a time, right? I mean, if you don't mind. Hello?
Yes. I'm on board.
In this one, you clearly mentioned it is DWNT, means it is double wall carbon nanotubes, right?
That's right. Yes, that's right.
These
are multi-wall carbon nanotube, and these are functionalized with amino group NH2. Yes, so these were double wall carbon nanotubes which are functionalized with NH2.
Okay. The last question. For example, we have you have considered about all the exterior parts of the, aircraft and everything. What was the case about landing gears? Because they are also a crucial part in aircraft, where they will face more fatigue the same way, more mechanical problems and issues. So what about replacing the conventional titanium alloy with the plastic?
Yeah, I think, Dr. Sylvester, whenever you have a new technology like this in place, the ethos of at the time when they were making this technology, I was involved in some very senior press briefings. At that time, the technology was very expensive, and if you look at whenever you're making a change of materials technology, yes, it's a very expensive move, and the pure intention at that time was to introduce an alternate a material, despite of the economics, despite of the cost, because the strategy was long term for sure. There's a saving to planet, to other stakeholders of the process. You're very right. I mean, landing gear is one of the most critical part, and initially, if you the part I missed initially, well before A350, the wing box of A380 was always made of carbon fiber. So they actually piloted the technology by implementing a sort of a proof of concept model by launching A380 first, by making its wing box of carbon fiber polymer material. And once they realize it's a successful technology, it has no issues, no accidents, God forbid, that's how they came onto this A350. But the landing gear still remains the most critical part, and it is still very much metal, to the best of my understanding. And not in the near future, there are plans as such to replace, because that is the only part. That's the part which is only used for on average from 5 to 10 minutes, if you think about the landing and if you think about the takeoff events. And that still remains quite critical. You need to have metallic material, and it is not just a structural part. It has to sustain high impact forces upon landing, and at the same time, it needs to also have very good fatigue resistance. So whenever it comes to impact resistance, the material is not good, and that's why if you look at the leading surfaces, they're not using the carbon fiber because it contains plastic, and plastic itself have environmental degradation issues in long run. But you have made a good point. If you look at the technology, the material substitution, it's still not that easy. So they would still be using the metallic part as such. Hope that answers
you
the
very much.
question.
Thank you very
Thank you.
much, sir. It was a wonderful lecture, and many concepts by Professor Michael Ashby, material selection. That many concepts you you made me to recap. Thank you very much.
Thank you. Yes, Professor Ashby is still very much active in here in Cambridge,
Yes.
and I'm sure you're using his software that was made by Granta, the material selector, CES material selector. It's again a great software, and they have actually got all these examples for good for students. You know, the Ashby diagram and the material selection charts and all that. I think they are there. It's very beneficial for everyone.
Exactly.
Thank you. Thank you.
Thank you very much, sir. Thank you.
We have more questions.
Yeah, we'll take few more questions. Anybody else? You have questions? Please open up now. Any more questions?
Sir, I'm Surya Kumari.
Yeah, ma'am. Go ahead. Go ahead.
Sir, I'm Surya Kumari from School of Engineering. Wear resistance and tribological behavior of carbon reinforced composite also important. How about this tribological behavior of these composites, sir?
Yes, tribology is very important. Surface properties, the wind resistance, the friction. Of course, if you are landing for example, in Middle Eastern climate, there's quite a lot of silica particles that can actually cause wear resistance. When it comes to tribological features of this technology, sorry I didn't get your name. You are actually relying on your paint technology, and that's why you will never find this technology still contains a few micrometer of paint, which is looking after the tribological aspects of this product. So it is important. I think what because you're dealing with epoxy, it is a chemical. What epoxy offers that it's very easy to add different stabilizers, to add different chemicals at the time of processing epoxy, and you can make it stick very well with your paint and coatings, which is looking after the tribological affairs of this product. So I think yes, that is all being looked after. And even if you have, because as a researcher in epoxy in particular, there's quite a lot of research. Even if you have to fly this product without using any coatings, for instance, you can still improve the tribological features of this great versatile chemical purely because there's so much this technology could offer. Hope that answers the question.
Thank you, sir.
Okay. I'm just conscious of the time. So
Yeah.
I'll
We'll quickly have only
question.
one more question if there is any. Otherwise, only one more question. Anybody is having?
Dr. Jayaprakash.
This is Vinod.
One by one. Like maybe first Dr. Jay Prakash can ask, then we'll give opportunity to Mr. Vinod. Yeah.
Professor, work is really impressed us and really very good innovation one. My question is that you fabric is honeycomb type.
I'm sorry. I think you're breaking quite a lot.
Structure for composite.
No, if I can tell his question, if I can tell his question, like he's asking about the scope of making this composites.
Okay,
Like,
I mean it's very much in action to our respected audience, the gentleman who asked the question, so I didn't get the name. It's very much in action. If you look at the sports products in particular, recently one of the rackets used by Roger Federer, the tennis player, they all are using carbon nanotube reinforced products. Apart from aviation industry, these products are also used in microelectronics. But Airbus, without informing other corporate details, they have actually employed the utilization of nanomaterials into the structural applications for that. So it's very much there. It's purely because microcarbon fiber and nanocarbon fiber, they go along very well. And epoxy itself is made up of carbon and hydrogen bond. Again, the chemical compatibility is excellent. And that's why these technology are very much in existence. They're not very much open about the utilization of nanomaterials because of various reasons, but it's pretty much out there. Thank you very much. Do we have any more questions?
There is one more question from Mr. Vinod. Maybe that will be the last question. We'll wind up after that. Mr. Vinod, go ahead with your question.
My question
Mr.
is
Vinod?
regarding.
Yeah.
I'm audible?
Yeah, go ahead. Go ahead.
Yeah, as door panels are involved, should not be composites used. There are some criteria. Hello?
Yes, I think again you're breaking for me.
Sorry.
Can you make your question clear, Mr. Vinod? Yeah. Can you make your question a little bit clear? Yeah.
Okay. I heard about some critical regions in the Airbus, in the front window panel and those places, carbon fibers must not be used. And I heard there should be only aluminum. And now in the new technology, alternatives research for that.
I think if I got your question right, you're talking about alternate materials that could actually take up the critical areas. I mean, yes, substitution of new material, it takes 10 to 15 years for sure, no doubt about it. And it contains, especially in aviation industry, if you look at the incident of Concorde, which was again a British innovation. There was one incident of the aircraft, and they decided to ground it for good. And that is the problem. If there would have been an incident, or there would have been an incident utilized by using this commercial product, this technology would have concluded its journey. So substitution is always looked as a very there's a lot of bureaucracy, there's a lot of red tape, there's a lot of research, there's a lot of unsuccessful projects, there's a lot of project failures, and then you come up with new substitutions. So it's never that easy. But you're right, sky is the limit. You need to start from your labs and transform into a knowledge transfer project, and work with SMEs and bring up a proof of concept, protected via a patent for perhaps, and then pitch the idea to these big dragons who are always looking for such ventures. I hope that answers the question. Thank you very much.
Yeah. Yeah, thank you,
Thank you
Dr.
very much.
Fawad. It was really a wonderful presentation, and thank you very much for joining us today and giving a talk in our SSE talk series. Have a good day to you. Take care.
Okay, thank you. Bye-bye.
Yeah, bye.